We should begin every recording with one of Jono's tunes.
A Jono tune?
Yeah.
Yes. Cool. I realised the last few lectures have been a bit short, so I've gone back, I've moved, shifted everything up. So it does actually mean at this point we're going to have some extra lectures spare. So I might do a little bit of map reduce, I might do some EM algorithm, and I might do some deep learning. But if there's anything you particularly within the advanced data science really want to know, let me know, and I will include it. I mean, we're basically at this point going to cover at least 2 textbooks and then start on a 3rd. So you'll have a reasonable amount of material done. Assignments, everyone did really, really well. Congratulations, that's all nice. Your next assignment's up if you want to have a go. You have 4 weeks to do it. Remember, you get 2 weeks for each assignment. We shove in a 2-week break. I don't count that as part of your time for working, so you've got 2 weeks plus 2 weeks holiday. So, you know, you've got to do some research at some point. It seems most of you are doing honours and MPhils. So, given all that, as always, if you have any problems, come and see me. I do have to warn you that the consulting session on the Friday of the day that it's due, I won't be here on that Friday. I'd like to say it's because I'm going to do really important things, but it's my 50th birthday and I'm going across to Melbourne to see the Cursed Child Part 1 and Part 2. But if Gary asks, it's a very important conference, just in case. And if anyone happens to know anyone who's important within the school, again, it's a very important conference. I'm not going to Melbourne just to drink alcohol and watch Cursed Child Part 1 and Part 2.
Those tickets are hard to come by.
I must have been just lucky. Yeah, they're very expensive.
Yeah.
Yes.
It's 50th, so you know.
Yeah, it's 50th. You do get a chance of when your wife says, "What would you like for your birthday?" And I went, "Something really, really mature. I'd like to go and see the Cursed Child Part 1 and Part 2." Cool. So we've been looking at this idea of how do we deal with non-linear data. And so far we've been looking at splines mainly, and we started with cubic splines. So this is the idea, we broke it down into bins. Within each section we fitted a cubic, and then we said, well, it'd be nice if our line that we fitted looks nice, basically. We want it to look smooth. So we made it continuous, so the ends met and the way we broke it is we had these things called knots, which is where we split it. And then we said, fine, we find that once you get to a cubic, the human eye sees that is smooth enough, and we will have it continuous both in its value, in its first derivative, and its second derivative. So you got this. And then we discussed the fact that towards the edges, you find that your cubic spline has a lot of variability. So the way we dealt with that is he said, we will, once you get to the extremes, the bins on the far left and the far right, we will just constrain that. Instead of it being a cubic, we'll constrain it to be linear. And we call this a natural spline. So once you have piecewise cubic that is continuous up to the second derivative and it's linear at the endpoints, we call that a natural spline. Okay. So today we're going to look at smoothing splines. So what's our goal? What we want to do is we want to find a function that fits our data really well. So what we want to do is we want to choose out of all the possible functions you could have, something that when you take the observed value yi minus the value that you fit from that function, you square it, you add them all up. We want to get that as small as possible. And obviously the problem is at the moment with this unconstrained problem, as soon as you do that, your best thing to do would be to find a function that goes through every single point. So completely interpolates it. So what we're going to do is we're going to add some extra constraints to make this a bit nicer. So the constraints we add is we say we would like our function to be smooth. And what do we mean by smooth? We mean that if we take the second derivative and we square it and we integrate that, that's going to be a measure of our smoothness. So it's how much is that thing sort of wiggly, and we're going to have a tuning parameter that's going to try and make that as less wiggly as possible. Okay? So again, it looks very similar to a lot of stuff we've seen before. You have a measure of fit, which is that first term, and then you're penalizing. You're adding a penalty term. And in this one, our penalty term is we're going to integrate over our values the second derivative of our function. Our lambda is going to be a tuning parameter. So as that gets larger, it becomes smoother and smoother. So as I said, this is a loss term. and a penalty term. Now, it can be shown that if you actually sat down and started to solve this problem, what you actually get out is a natural cubic spline, where your knots are at all the unique values of your, and at this moment we're looking at a univariate case, your unique values of your predictor. I can tell you to prove that takes me approximately 2 hours, because I did it yesterday because I needed a set of solutions for your assignment. So some good news and bad news. Yeah. So guess what the first question of assignment 4 is?
So we're not doing any research in the holidays, then you put yourself in.
No, you don't get assignment 4 till after the holidays. Yeah. The second half semester, no research at all. Now, I've scaffolded it quite nicely. I've broken it down, so it should be okay. Hopefully. If I can do it, let's face it, you should be able to do it. Okay. So let's think about it. A smoothing spline has n parameters, because you've got this cubic. We know that a natural spline has the number of parameters equal to the number of knots. We've just gone and fitted a natural cubic with basically a knot for every individual value. So you should have n degrees of freedom. But what we find is you actually end up getting, because of the smoothing parameter constraints, instead of getting the n degrees of freedom, you get slightly less. And we're going to call this slightly less effective degrees of freedom. So theoretically, you should have n, but we add in this smoothing parameter, and we end up with less degrees of freedom. And we're going to call this effective degrees of freedom. So how do we get this effective degrees of freedom? Well, if you think about it, you could imagine that once you've fitted your smoothing spline, what you've got is this matrix that will take each of your values and give you your fitted value. So we're going to call this the given values. That's going to be a vector of length n times 1, g hat lambda. And you can imagine that you've just got this mapping matrix, this linear transformation that takes all your data and converts it into the mapped data. So, I mean, we've designed this by describing it as the optimization to a function. But eventually, once you've finished that, you can go, my function will return a value for each of my observed values. So you can imagine this is just a linear transformation. You've got a vector. And that's, sorry, not a vector, a matrix. So I'm going to denote that matrix as S lambda. So that maps from my data to the fitted values, and it's an n by n. So as I said, S lambda is a n by n matrix. And we're going to define the effective degrees of freedom is going to be, I'm going to add up all the values on the diagonal, i.e. our effective degrees of freedom will be the trace. So if I have 4 rank in this matrix, the degrees of freedom would be n. But because I don't have 4 rank, I'm getting something that's less than n. And I get that from the trace of my matrix. So this is a standard definition of effective degrees of freedom. With all these processes, you can end up with this matrix that's mapping across, and you can look at the trace of that matrix, and that will give you effective degrees of freedom. Who would think, what about the leave one out cross-validation? Well, remember, once we had linear regression, we had this really quick way. So let's remind ourselves, what's leave one out cross-validation? The general idea is I take my data, I remove a single data point, I fit my model on all the other data, and then I use that model to predict the value I removed. And I repeat that for n observations. And then what I do is I look at the difference between my observed value and the fitted value for observed value based on all the other data. I square it, I add them all up, that gives me my cross-validation error. In the last assignment, you showed that in the case of your multiple linear regression, there's a quick shortcut. You just actually took the residual sum of squares from your full model and you adjusted it by your 1 minus your HII. So you looked at your projection matrix and you got it from that. You have a very similar thing when it comes to smoothing splines. So ideally what I'd like to do to get the residual sum of squares of my cross-validation for leave one out, I'd like to take my yi minus the fitted value for yi based on the model with the yi term taken out. But again, you can see this is actually yi minus the fitted value from my full model over 1 minus, again, you've got this similar idea. Before we had our H, which had our projection matrix. Now in terms of our smoothing spline, we've got this S. So you can just use the diagonal from that. So, and hopefully you can see the sort of analogy between the two that you've seen so far. I'm not going to make you prove this one. You're going to spend at least, 2-3 days just doing that previous slide. This really, eventually your supervisor will take me aside and beat me with the penguin stick that they obviously have.
It'll be an exam though, right?
Well, the penguin stick, oh yeah. Anyone can do my exam, but doing it with a threat of me just every so often, just going with a penguin stick. We didn't mention the penguin stick at the start of this recording, did we? So there's going to be people at home now just going, what the fuck? There's a question on the penguin stick in the exam? We apologise. So let's actually use this smoothing spline. So we're going to go back to the wages data. It's the classic one from the James book, so I'm continuing that. So we've got the wages of a variety of people, and we have predictors, things like what year it was, their age, their marital status, their race, their education, etc. And what we're trying to do is we're trying to predict. But the main thing we're interested in at the moment is, if you notice in all the splines I've stuck with a single univariate. After the break we'll start looking at multivariate. But we want to look at the relationship between wage and age. And we know that it's a non-linear relationship. So, there's a couple of ways you can do it. You can actually just use the smooth spline function. So here I give the x and the y, and I can say how many degrees of freedom I want to spend. So it's going to go and it's going to explore. You can say this is how many. But of course, what you could do instead is you could choose different tuning parameters to try and get the best fit with cross-validation. And the way you do that, again, use smooth spline. You give your x and your y, and you say cross-validation equals true. And it goes off and it does it. So here is I can't remember if it's the first one. It's the first one, not the cross-validation. It returns a function now. You can see the degrees of freedom are given. The equivalent degrees of freedom or effective degrees of freedom is your 17.00237. If I actually look at the degrees of freedom on the one where I fitted with the cross-validation, it decided that the best effective degrees of freedom by choosing the appropriate lambda was 6.794596. Okay?
Was there a reason you chose 17 or just to be something different than 6.8?
Something different than 6.8. And also, to be consistent, a lot of these examples are also done in the James et al. Textbook that I've been following. So if at any point you sort of go, I want to, for some reason, foolish reason, Jono's explanation is not perfect, you go, I should read around this. Then when you go to James, it matches exactly. So. The other thing is you can actually get all your values from that S matrix. It calls it LEV for leverage. And in this case, I've just got them out for the first one. And then if I take the sum of that, so these are the values from the diagonal of that smoothing matrix. You can see this matches the effective degrees of freedom. And here's my two smooth functions. This is the one where I did the degrees of freedom 17 is the blue one, and the cross-validation one is there. And they match a lot, and you'd go for the cross-validation one. And when we get to GAMS, you think about general additive models, which is basically now taking these and putting them all together. When we get to GAMS, you'll see that you're sort of almost saying, well, I've got so many degrees of freedom. How many should I spend on the age parameter? The age parameter, the age predictor, etc.
Is there a quick reason why this is a 61 by 61 matrix with 17 degrees of freedom? How did the matrix get to be that size?
It should be for the number of observations.
Okay, right.
There should be, as long as they might have removed some missing values, but there should have been 61 observations.
It's like more than 61 to me.
Yeah, but it might not be 61 unique values.
Okay.
So now we're going to look at loess. To be honest, out of all the ones I've talked about so far, I've used almost none of them. Loess is the one that I find the one I go to all the time. And mainly because loess is pretty well the built in. If you ever go G on smooth in ggplot2, it defaults to loess. A lot of also the early work I did my PhD on microarrays, they standardly use loess. So
These slides aren't on the course material.
they weren't until Monday night. I decided to shift everything.
I just downloaded it again and it stops here.
They're not on the website.
Yeah.
No.
It
Oh.
only has the first 14 slides.
I should have them.
You can fix it later if you need.
Yeah, just.
You sure?
Yeah.
Okay.
It'd be nice if I could annotate them as you speak that.
Yeah, sorry.
Yeah.
It's all pretty pitchy.
Yeah.
Yeah, they will be. I did update it this morning, but maybe I haven't pushed it on the Git. So, loess. Okay, so let's go back to the KNN, so the K nearest neighbours. So remember the K nearest neighbours, what we're trying to do is get our Bayesian classifier. So we want to estimate the probability that Y equals class J, so this is in the classification problem, given our predictor X equals X0. And the way we did it is we empirically got that distribution, we found everything that was close to an individual point, and then we did a majority vote type classification. So we counted how many were actually of class J, and then we averaged that. And then we just, remember to get the optimal classifier, we just assign to the most common class in your neighborhood. Okay? What about regression? Well, what you could do now is you could, in your regression, you could find a predictor X0. You could find the points that are closest to it. So you could look at your K neighborhood. And then now you could set your predictive value to be the average of the response variable for those points that are within the neighborhood. Okay? So you get your X0, you say, right, in case my age is, as we know, nearly 50, maybe I find everyone who's close to me, find their average salary, and that will be the prediction for Jono. So here's my function to do that. Just so you've got it, notice, so this takes an X0, takes some training data, takes the K for the size. So I take my training data, I calculate my distance, I'm doing the Euclidean distance. I then take the top values, the top K values, on a negative distance because I want to be close. That negative, again, if anyone wants to know where my life goes, that negative took me about an hour to realise it should be there. Just, it wouldn't work. I didn't have the distance, I was actually doing the K nearest neighbours on the ones that weren't close. Yeah, yeah.
K's furthest neighbours?
Yeah,
Yeah,
yeah, a new
that's
approach that turns out to be a little bit shit.
It's going to take the top of the distance.
Yeah,
The furthest
yeah. It took me ages, couldn't get my code to work. Yeah, eventually you put a negative in. About an hour, I'd say, about an hour to work out one character in my code. Yeah, that's my life. So then I summarize by getting the mean of them, then I pull that. So remember, pull will just actually grab a column out for you and return it as a vector. Very nice little thing if you ever want to do that. The old school used to be dot, dollar, and then the value. Pull's a bit nicer. And then I return it. Now the problem with this function at the moment is it just does a single point. So if you don't know, you can actually vectorize any function in R by using the vectorize. So this vectorized thing will take a function, my KNN. Is this new?
Well, here we go.
That's
Some
awesome.
fun facts.
You just, for the first time ever, I've actually said R code where you actually went, I didn't know that.
That's
I'm impressed.
ridiculous.
Yeah, it's great. You'd have to say what you want to vectorize over, and you can vectorize over multiple parameters as well. But in this case, I want to vectorize this function by just X0. It's great, isn't it?
I would have had to like turn it into a function and then somehow turn it into a list to then map over it with the.
Yeah. But yeah, vectorized function is really, really nice if you've not discovered it. And it just now, I've renamed it. I often use uppercase for the vectorize and lowercase for the not. but now I've got a k-n function which will now take in multiple values. So the vectorizing is really lovely. And here's my version. Here's some simulated data, and here is my fitted values. You can see that it's too jiggery, it's probably, or wiggly, or it's just a little bit rubbish, because what happens is you basically go along, and for a long time you pretty well sit where you are, and then suddenly a point comes in and one point goes out, and it suddenly drops, and then your window moves along and a point goes out, and you just jump up and down.
What's your value for k?
I can't remember off the top of my head.
It's alright then.
Sorry, it would have been
3 or something.
3 or 4, something like that. I can't remember. But it's really, really wiggly. So how can we improve that? The question is, how can we take that? It's a good idea to start off with, the nearest neighbours, you know. The idea of all empirical or non-parametric is the data is the model. How can I improve that? How can I make it smoother? So let's start doing it. We're going to start with the, I did try saying these, but let me have a go. Nadaraya Watson kernel weighted average. Thank you. So at the moment, we have this window. You're basically going along, and as soon as you get in that window, you're in. And once you're out, you're out. That's it. It's basically you're either in this window or you're not. So what we're going to do is we're going to have a window that sort of says, the closer you are to the middle of the window, the more we're going to take your value. We're going to wait. So as you get further away, you don't just go along and then bang, you disappear. You slowly drift out. So what we're going to do now, if you look at that first one, now our fitted value is a weighted mean. So I'm adding up, but now I've got these weights. These weights are k lambda x0 xi. So I take your value, but I weight it. That is just a weighted mean by how close you are to that point. So we have to decide some sort of weighting mechanism. So the first one we're going to do, if you think Watson was difficult for me, wait for this one. Epanechnikov. No?
Epanechnikov?
Epanechnikov.
Epanechnikov?
A Epanechnikov is what happens where you cough, but you have food in your mouth and you start to panic a little bit. You go, oh, that's an Epanechnikov. I don't think that was that person's name.
Maybe his mum was eating whilst giving birth and had an Epanechnikov.
What's his name? Pretty well. Okay, we'll call him Epanechnikov. Because he was actually born in Manchester, so that's the only reason he could have such a complicated, or she could have such a complicated name. But they invented, after they got over the fact that their mother choked during childbirth, they eventually invented a quadratic kernel. So what's this quadratic kernel? First of all, we're going to have a distance metric, so dt. Our distance metric is this 3/4 1 minus t squared. But it's a step process. If your value of t is within basically -1 to 1, you get that. Outside, you're just 0. So we're waiting that once you get outside of this distance, you're just going down to 0. What we're going to do is we're going to take the absolute value between any value x and x0, and we've got a scaling parameter of lambda. Okay. So what does it look like? Well, first of all, let's write some code. So here's my quadratic kernel. A particular quadratic kernel. I don't like to just be very specific on naming them. And that will take an x, an x0, and a lambda. And does that calculation, I'm using my absolute value to get my t, and then my d, I'm just using an if-else. Remember, if you ever need to vectorize an if function, your if-else does the vectorization automatically for you. So here are some illustrations of this function, some visualizations. So your x0 is the value you're going to maximize it. These are symmetric around your x0. And the lambda changes as the lambda, as you can see, decreases. That's the amount of, it basically squashes it in. So you can see it's symmetric around your x0 value, and the lambda changes, and this is the amount of weighting. So when you're very close to x0, you're going to have to be weighted 4, but as you get further and further away, the weighting decreases down till eventually you hit a point you're not in that at all. Basically, points that. So it's like that window. But now, we don't define a window, we just say once you get too far away, you just have a weighting of 0. So just having difficulty. Nadaraya's Watson, I now put that all together. So again, takes an x0, a train, and a lamb. It calculates my k by using my quadratic kernel, no problem. And then it calculates my ky, and now I can return the sum of the ky's over the sum of the k, so that is my weighted mean. I could have done this directly with, the mean function has weights built into it if you want to. I now vectorize that again because I want to be able to give it lots and lots of values. And here it is. So the red is the one we had before, the KNN. And the main problem we had was it was just too wiggly. This now, you can see it's a smooth version of that. It's just using this window that's drifting across. All the values in the center of the window get weighted more, but it's still calculating a mean. To some extent, it's calculating this moving average across that's just been smoothed to take more notice of points very close to where you're predicting for and less as you get further away. Okay?
Did you have the MSEs for both of those?
No, no, sorry. Didn't calculate that. But you would use cross-validation or something like that to choose. You've got a tuning parameter now, that lambda. You could choose the different ones, and we'll discuss that later. Other functions, the ones I could find in Hasty and James, the tricube function. So now your d is 1 minus t cubed, and that whole thing is cubed, and again is defined for t within plus or minus 1. Both of these things basically have a structure that they weight a symmetric around x0, you get further away, and then they hit a point where you get to 0. The Gaussian doesn't actually get to 0, it gets to so small, but remember the probability density function of a Gaussian never actually hits 0, it only hits 0 at minus infinity and infinity. So these weight, but they weight, you know, it doesn't get to 0. In other words, if you look at the pictures here, you know, the blue line is the Gaussian, and that actually never gets to the point of hitting 0, while both the other two actually get to 0. Okay, what about we improve it? So at the moment, we've got this weighting function. We take a window across our data with this weighting function. The points that are close to the point we're trying to predict are weighted more, the ones further away are weighted less. But at the moment, we're just taking a weighted mean. But we could actually do exactly the same. Instead of having just this individual piecewise constant, we could actually fit, at that point, a linear regression. So I'm going to go to an individual point, I'm going to find all the data, and I'm going to fit a linear regression, but I'm going to weight that linear regression. So the points that are closer are used more in calculating linear regression than the ones further apart. So now what I'm doing is I'm going to go and I'm going to find the values of alpha and beta at my value I want to predict for in a weighted linear regression. Okay, so I find the values, and then for that point, I'm going to predict whatever the linear regression says. Then you go to your next point you want to predict. You get the points, the ones that are closer get weighted more, the ones further away get weighted less. You get your linear regression, you use that to predict your value. So for every point you want to predict, you have a fitted linear regression, and you're just stitching these together. And you're weighting so that points that are closer are better. So let's keep going. Why don't we just fit a polynomial regression? Why don't we go to our point and take all the things and just say, right, at this point I want to fit a polynomial, in this case of order d. So I could have a cubic, a quadratic, I could keep going. To be honest, you often don't. You often pretty well fit about the cubic again, because we know that has nice properties that the human eye sees that as reasonably smooth. And all you're doing is you're going to every point you want to fit, and you fit, for example, a cubic, but you fit a weighted cubic. So you take more notice of the points that are close to where you are and less that are further away. Once you've got that cubic for that point, you then say, what does this cubic predict for my value? That is my fitted value. Go to the next point, repeat it, and just keep doing it. So we don't do all that. It's done for us. There is a loess function. There is a loess function, which is an early one. Occasionally you'll see people talk about the loess, L-O-W-E-S-S. That is a very old function. The new one now is loess.
What does loess stand for?
I can't remember, I didn't look it up. But
Not
we will
really.
wait while Josh
Something
tells us.
smoothing spline.
Locally estimated scatterplot smoothing. And loess is locally weighted scatterplot
Yeah,
smoothing.
but now everything's loess. It's the default. Whenever you've gone plus G on smooth, 8 times out of 10, that is what is sitting. It will actually say loess with span equal to this. Okay. So I checked up loess. I didn't check up what it stood for, but I did find out that the default behavior is it uses the tricube kernel. You provide the span, the default span, and the default polynomial is a quadratic. So basically it's fitting quadratic, it goes along. You can actually set this, so you can say, here's my kernel, you get a choice of kernels, and you can also say the degree of the polynomial you want to fit.
Can you give it a custom kernel?
I'm sure you could. I'm sure you absolutely can.
Yeah, I don't know why you'd want to, but I'm sure
Yeah.
you could.
Good flex.
Good what?
Good flex.
Good flex?
Yeah.
What's good flex mean?
Gotta get with the kids, John.
No, I'm old now. I can't even get with my own generation, never mind the kids. So as always, let's do it. So we'll go back to the wage data, because why would we not? There's a point, I mean, it's all right for you, you just have to see it for a second. There's a point when I'm typing these slides, I go, I don't fucking care about the wages, just fuck. But anyway, it's consistent. So, wage, loess, you just do the loess function, wage, data, stuff like that. And it just spits out, and then you can use that to predict. One thing you should realize at this point is it's just diddly squat shit at actually explaining. It doesn't have, you can't at any point sort of go and say things like, well, what is that relationship? How does it work? This is now, you've lost that. You've got this beautiful way of actually having a fitted value to explain that data. But when you say, well, what's the model? The data is the model. That's the key idea with these splines, these non-parametric type methods. And here's your thing. So here's your relationship between wage and age. You can get standard errors, you get the whole thing. But how do we choose the right one? We've got, okay, let's assume we'll go with the default quadratic and the tricube. I still have to choose that lambda. I still have to choose the value to do there. And this actually was a problem I had to solve recently. We were looking at a very cool thing. Have I got? Yeah, I got enough time. So we were looking at a thing called PSMC. So here's the clever idea. Let's say I went and got all of your genomes. By looking at your genomes and the difference between you, I can actually look at the population tree of humans. By looking at the variability between individual genomes, I can look back in time and I can start to estimate things like, was there a bottleneck when we came out of Africa, etc. PSMC is a technique that we use now that just goes, well, actually, if you think about a single genome, some of it will come from your mother and some will come from your father. And some of the mother stuff will come from her mother or father, etc. So your individual genome can be actually thought of as a random sample of individuals. As long as you can sort of go along the genome and identify which bit came from your grandfather, which from your grandmother, or etc. You go, well, now I've actually got a load of samples. I can now use an individual genome to look at your population history. And these methods are called MSMC and PSMC. Okay? I can't remember off the top of my head what they stand for. So we were doing this. We actually, because often with ACAD, when they're looking at, for example, the genome of, and the one we were looking at was the Tasmanian tiger, there's not a lot of Tasmanian tigers. If you think we're bad with penguins, we were really bad with Tasmanian tigers.
Well, they ate our sheep.
So why did you kill the penguins then? Again, they might eat our sheep. You never know. So we have Tasmanian tiger samples that have been mummified. We use that. We look at the genome. But the problem is it's fragmented. So you've got this method that says, I can get away with not having multiple samples by having one good genome. Because we're at ACAD, they went, we don't have one good genome, we have a fragmented genome. Is this going to be a problem? So we, as always, said, well, let's find out. So we actually invented our own genome, we fitted the truth, we then fragmented it, we fitted our models, and we wanted to compare how bad your results got once you started fragmenting. But we needed a truth. We needed a population size over time from our genome. So we decided to use loess, but we needed to tune it. So here's my tuning code to do it. So the first thing is I managed to find a really nice paper that actually gave you a Epanechnikov information criterion, a corrected one. So I found that and I implemented this code here, which first of all, it takes a loess fit. First of all, because I'm going to be running this lots and lots of times. Remember, I want to have, we had thousands of genomes we simulated. For each one, I wanted to be able to just run it multiple times. As soon as you start doing things multiple times, you really want to start having try and catch loops in there. Because you don't want to start putting it on Phoenix and have it running and having it stop after 5 minutes going, yeah, I give up. You want it to go, 5 minutes in, I gave up and I spit out an answer for you, but the rest we kept going. So what this does here is it basically says, when I give it a fit, it says, look, if that's not a loess type thing, stop. So it's first of all saying, I know that only a loess will work, so if you're not that, just stop, and it will stop, and then I can catch the warnings from there. Then I've got my parameters to the fit. I can get the number of observations, I can get my trace from that function, I can get my sigma squared, and I can return this function, and that function there is the AIC corrected for loess, as given. And notice I actually, because I have to write this because I'm an idiot, I'm an angry idiot, and I will spend my whole time next time I come back to this in 6 months' time going, why the fuckity fuck did I use that formula? So my comments always tell me exactly where I got it from, and also I acknowledge the fact that the original idea of some of this code came from that person there. So write your comment as if an angry psychopath is going to look at your function in 6 months, because I do. So once I got that, I then wrote an auto loess tuning. So this basically, what it does is first of all, it checks to make sure it's a loess. And then I've got a function inside a function. So my function then does a very simple thing is I can give it a span. It will take that fit. I'm being a bit bad here because I'm not passing my fit in. I just know that the scope of this function will keep it safe. And I'm basically saying, take that fit and update it automatically with this particular value of the span. So what that function will do is it will take my fitted model, it will try a span, it will then shove it into my AIC and it will spit out an AIC value. Next thing I do now is I go, fine, optimize that. Find me the thing that minimizes my AIC corrected for different spans. Once I've got that value, now update my fit for that span, spit it out. So you start off with some loess, and it will go away and it will explore that space and spit out the best value of your span, but I don't really care about the span, it then spits out the lowest for that value of the span. It's really cool, it worked really nicely. And it works fast, which I needed because I had thousands. So here's an example, I took that wage loess, I basically hit my auto loess, and hopefully you can see that it's actually got the different spans. It started with a 0.85, ended up with a 0.75. I think you'll find the residual standard error is 39.9 there. 39.9 there. So I have no improved, but the equivalent number of parameters goes from 4.99 to 4.43. So we do have a little bit of improvement there. And there's my two things over one another, showing that they look pretty similar when it comes to it. That's it. Cool. Any questions? So next time we'll start GAMS, MARS, and NLS. So we'll actually start putting this together to get back to some model fitting. Cool. Now, obviously, we don't have any lectures for the next 2 weeks because it's the mid-semester break. So if you need to steam in that time, I will be around for the first week. The second week, I'm on annual leave. But, you know, even though I'm on annual leave, I still will be checking Slack and email. So if you do have questions, please feel free to send them to me. That's it. Any questions? Cool. I'll see you after the break. Have a good break.
Workshop?
So, oh, we have a workshop. No, this Friday. Yes. See you at the break. Except for the workshop, this Friday we're going to learn how to use data table, which you will need for the DNA methylation problem in your assignment. So, well worth coming along. Make sure you install what you need for data table. See you all Friday. Then we can talk about holidays. Thanks all.
Jonathan,
Yeah?
the previous 2 slides are choosing the span, right?
Yes.
Not the stan or the span.
Yeah, I know. I left that in. So you actually noticed my headings?
Yes. I looked up and I went, why are we looking at span?
I was bored. I put things in to see if anyone would notice. Well done. I wish I had chocolate frogs. I would actually give you chocolate frogs.
Another thing, I'd be quite happy if my next supervisor's meeting is Matt just beating you with a penguin stick.
The penguin stick.
Quite fine with that.
Thank you. I'll take that as an insult.
Will be more interesting than our usual meetings.
Yes.
So, John, for the PSMC,
Yes.
let's say you got one really high quality genome.
Yes.
How do you know when to chop it up and say that's
We use a hidden Markov model.
okay?
So we work on the principle that you have to estimate your recombination points. So we use a hidden Markov model. So you can do this hidden Markov model where you say that your level is whereabouts that segment is from,
Yeah.
and then you can do the emission of your diversity from that. So yes, it's using a hidden Markov model.
Okay.
So hidden Markov model, you've got a Markov chain, and the state of the Markov chain then gives you the probability density for your actual observed values.
Mm-hmm.
And you never observe the state of the chain, you observe the values. So the classic one with hidden Markov models is what they call the crooked casino. Imagine you have a casino
Yep.
that has 2 dice.
Mm-hmm.
One is your standard 1 to 6, all fine. The other one comes at 1 half the time, and the other one's the rest of the, split evenly. And what they do is they don't tell you, but they basically toss a coin.
Mm-hmm.
And every time they toss the coin, if it's a head, they move to the crooked die. If it's a tail, they stay.
Mm-hmm.
And they do that every time. Then they roll the die. Then they toss the coin. They roll the die. But all you see is the die rolls.
Mm-hmm.
How do you actually work out whether there's a crooked die, the probability, how they're choosing the states, that whole thing? And you can do that with what we call a hidden Markov model. And underneath it is doing an EM algorithm. EM algorithm, if we get time, we'll do in this course, but basically it's the classic method you use where you have missing information. In this case, your missing information is, I don't know which die is being rolled. Because if you knew the die, it would be easy, wouldn't it? Because if you knew how the die moved, you can estimate the probability of moving. It's just a Markov chain, you observe it. Also, if you knew the die, you can work out the probability of the crooked die of getting 1s, etc., because you can observe it long enough. You don't know that missing information. EM algorithm lets you complete the data and go from there.
Okay.
And if we have time in this course, it's one of the things I would consider adding is just a lecture or two on not hidden Markov models, but the EM algorithm.
Yeah.
Okay, so particularly useful method.
Yeah. Hidden Markov models in stochastic position theory, isn't it?
Yes.
Yeah. I should probably learn that at some point.